Welcome to qnawire.
Hi, so in this problem, what we are thinking about is the titration of a weak acid with a strong base. So, the information that is given to us over here is that the initial concentration is 10 to the minus 4 molar, and the pKa is equal to 5. So now, we're missing some information regarding the amount of titrant that is being added to the solution, so I'm just going to give you the general idea of what needs to be done in all of these cases. So, before the equivalence point, and in general, the reaction that you're actually looking at is the following. You have the weak acid that, in the presence of the strong base, in this case sodium hydroxide, is going to produce the conjugate base, A minus, plus water. So, before the equivalence point, if we are starting with an initial concentration of C0, our ice table looks like this before equivalence point. You're going to add a fraction x of OH minus that is going to be smaller than C0. So you're going to have a change on HA minus on the weak acid of minus x, and you're going to produce plus x of the conjugate base. That means that at equilibrium, the concentration is going to be C0 minus x, something close to 0, or effectively 0, and over here you're going to have a concentration equal to x. Before the equivalence point, what we're going to have is a combination of an weak acid with its conjugate base. So the pH is given by the Henderson-Hasselbalch equation that tells us that pH is equal to pKa plus the logarithm of the concentration of A minus divided by the concentration of HA. So, in your question, you ask what is this ratio of concentration? What is A minus divided by HA? And as I mentioned, that is going to depend on the amount of base that you added. In this case, since I consider this to be X, and remember, all of this is in terms of concentrations, all of this is in terms of molarity, this would be equal to pKa plus logarithm of A minus has a concentration of X, and HA is going to have a concentration of C0 minus X. So, in order to know what is the actual pH, you need to have information on how much of the base you actually added. Now, the other possibility that you have is what is going to happen when you reach the equivalence point. So, at the equivalence point, what you have done is that you added the same amount of OH minus as the initial concentration that you have, producing A minus plus H2O. Okay? So, for this case, what I'm going to do is write down the ice table, but now in terms of mole instead of terms of concentration, because you know what is the initial amount of mole that you have of your weak acid, and you're going to know what is the amount of mole of OH minus that you need to add. But the total volume is going to depend on the concentration of the base. So, in this case, your ice table at the equivalence point looks like this. N0 is going to be my initial amount of mole of HA. So, we're going to add the same amount. The change is minus N0. Over here, 0 and water doesn't matter, plus N0. So, of HA, I'm going to have something close to 0, something close to 0, and I am only going to have, in principle, A minus, correct? But this is not correct. Let's remember that a weak acid can react with water. So, at the equivalence point, we're going to add a different equilibrium that corresponds to A minus plus water, producing HA plus OH minus. And the pH is going to be given by the concentration of OH minus that we're going to find. So, in this scenario, your ice table is going to look like this. you're going to start with N0. Water, again, is a pure substance. It doesn't matter. The amount of change, we're going to call this fraction x plus x. So at equilibrium, you're going to have N0 minus x, and x. Now, this reaction corresponds to the Kb of the weak acid, or of the conjugate base, however you want to look at it. And by definition, this is the concentration of Ha times the concentration of OH minus divided by the concentration of A minus. If we replace the values that we find here, you're going to see that this becomes x times x divided by N0 minus x. And all of them need to be divided by the total volume in order to get the proper concentrations. So you are going to need to solve for this equation. This becomes a quadratic expression. And actually, just for sake of simplicity, let's rename this as, using x over bt, let's call this now Cx to denote that this is the concentration for x. So this becomes Cx times concentration in x divided by N0 over Bt. This is going to be concentration at the equilibrium point minus Cx. Okay? Where I use N0 over Bt, it's going to be C of equilibrium. So now what you need to do is solve the quadratic expression for Cx. As you can see, this becomes Kb is equal to Cx squared divided by, actually, C0, just to keep everything consistent, divided by C0 minus Cx. You need to solve this quadratic expression. And how do you find Kb? Well, we know that Ka times Kb is equal to Kw, which is 10 to the minus 14. So in this way, you can solve your problem by solving this quadratic expression. Now the pH is going to be given by the concentration of OH minus, which is the value of Cx that you're going to find. So the pOH will be the minus logarithm of that. And the pH would be 14 minus pOH. Now, the other possible simplification that you have is that if N0 over the total volume is much larger than X over the total volume, your equation actually reduces to Kb is equal to Cx squared over C0. So you can find the result for Cx directly as the square root of Kb times C0. And this is the value that you can use for finding the concentration. And that would be all. Thank you very much.